So let's turn to benzene chemistry and look at some electrophilic aromatic substitution reactions. We're going to look at 3 examples in this video. First one's going to be a bromination with iron bromide, using the iron bromide as a Lewis acid catalyst. Then nitration, using sulfuric acid as a catalyst. And then sulfonation, using sulfur trioxide in sulfuric acid. So let's look at the first one, which is the bromination of benzene. Now, to try and get things started, we need to compensate for the fact that a benzene ring itself isn't a particularly strong nucleophile. So we can help things by making a better electrophile. So the bromine with the iron bromide can form a complex to the iron bromide. And that iron bromide complex, of course, puts a positive charge on the bromine. Bromine being more electronegative, it doesn't like that, so it can break that next door neighbor bromine to bromine bond, taking the electrons, and we finish up with this ion pair between the bromonium ion that's formed and the iron tetrabromide anion. Now that bromonium ion is now a much better electrophile because it's so electron needy with that formal positive charge. So going back to that benzene, now with the bromonium ion produced in solution, the aromatic ring can use a pair of electrons to pick up the bromonium ion, forming a new chemical bond. That, of course, creates a positive charge on the apex carbon at the top. It's still sp2 hybridized, but now that atomic orbital above and below the ring is now empty. But it's still overlapping with its neighboring atomic orbitals, and so those electrons in the ring can move around as we form resonance structures. Next one, again with that empty atomic orbital, now moved 2 carbons down to its new position. Electrons swing around again from the neighboring atomic orbital to create a third and final resonance structure. Now, of course, to finish off the reaction, we need to get rid of that positive charge. And we've got that iron tetrabromide, which can, oops, I get my arrow correct, it can use the bromine to iron bond, break it, as the bromide breaks off, picking up the hydrogen to form hydrogen bromide as a side product, and the electrons from that carbon to hydrogen bond can be used to plug in that gap and complete the aromaticity of our final product. Our bromobenzene with side products of the hydrogen bromide and of course the Lewis acid catalyst of the iron bromide. So let's look at the nitration reaction now and follow it through. Similar to what we just saw with the bromination, we're interested in making a better electrophile because our aromatic ring benzene isn't all that great of a nucleophile to begin with. So with nitric acid and sulfuric acid, the nitric acid can pick up a proton from the sulfuric acid, and then the electrons in that oxygen to hydrogen bond retreat back to the sulfuric acid. And we produce this excellent leaving group on the nitric acid, H2O+. And so that more electronegative oxygen isn't going to stand for that, and it's going to pull those electrons away, and we'll produce the nitrosium ion. Again, the nitrogen to oxygen bond is breaking as the oxygen, positively charged formally, although it's not shown here, pulls the electrons away. And to complete the octet of the nitrogen, the electron lone pair from the oxygen comes in to make that octet once more. But realize that the nitrogen is positively charged, making it electron hungry and a much better electrophile. So now, while this has been going on in the mixture, if we bring in the benzene, it can use its electrons to attack that improved electrophile, because that would cause an octet rule break if the nitrogen to oxygen pi bond didn't break with it. And we attach the nitro group to the ring, but of course it's not aromatic at the moment because of that sp2 hybridized carbon with an empty atomic orbital above and below the ring. But it's stabilized by resonance as pi electrons move around to plug in that gap each time, moving around the charge as electrons move around, and we can produce 3 resonance structures. Now, to finish off the reaction, we have to restore aromatic nature. So the hydrogen sulfate, the conjugate form of the sulfuric acid, can use a pair of electrons on the oxygen, picking that proton back up that it originally lost to the nitric acid. And the electrons in that carbon to hydrogen bond are returned to the ring to restore the aromatic nature. And we get a final nitrobenzene product and a catalytic sulfuric acid returned. So our last reaction of the day, the sulfonation. Again, we'd like to have a better electrophile, so we need to make that magic happen. So we'll take some sulfur trioxide together with sulfuric acid, and the sulfur trioxide can pick up a proton, and it leaves us with a central sulfur atom which is positively charged, electron needy, and therefore a better electrophile. We bring in the aromatic benzene, and then the benzene ring can use its pi electrons to form a bond to the sulfonyl group. That attachment to the ring causes a positive charge on that bottom carbon atom, which will have an empty atomic orbital above and below the ring. But again, that instability is helped because of the resonance forms that we can draw as the electrons flow and move around the carbon ring, moving around these atomic orbitals above and below the plane of the ring. So the electrons move again, trying to plug in that positive charge, and we get 3 resonance forms in total. Then for the finish of the reaction, we need to get rid of that hydrogen, which is on the same carbon as the sulfonyl group. Remember, it's supposed to be a substitution reaction. So it's the hydrogen which is being substituted off using an electron pair from the conjugate of the sulfuric acid, the hydrogen sulfate. And we can close in that electron gap by using the carbon to hydrogen bond electrons and get our final product. Notice that the reaction overall is reversible, and so we have to watch out for aqueous acidic conditions when this group is on. Otherwise, we could unravel the entire product back to the original starting aromatic. But more about that later, because we can actually use this to our advantage by using a sulfonyl group as a temporary protecting group in later reactions.